equations by the graphing method. So this is our first of our three methods. All right, so what is a system of equations? Since this is our first method, this is time to introduce the whole concept. So a system of equations is, for our purposes, going to be defined as two or more equations solved together. Okay, the solution. Now, the word solution in certain situations might just sound like the answer, but in this situation, it has a specific meaning. Just like in a chemistry class, a solution is when you have one substance dissolved in another. So for us, a solution here is the point of intersection of both equations, and the x and y values that make both equations true. I guess I should technically say all equations, but we're going to be sticking with two equations. But in upper level mathematics courses, you might actually see three or more equations solved together. Okay, so let's go ahead and talk about the three types of a system of equations. Let me pop over here. Okay, I've got my color set. All right, so we could have intersecting lines. So as that might sound, that would be a situation where we have one line and another line, and they intersect somewhere, and this point here, that is the solution. There's an x comma y value for that point, and that's the solution. So when there's intersecting lines, there is only one solution. We are talking about mathematical lines here, and we're talking about linear systems in this chapter, so there's only one place where these two lines will intersect. We could, however, have parallel lines, and so first line, and I'll do my best, not the best, pretend that is parallel. So we have our second line here, and it is parallel to the first line, so where do they intersect? Nowhere. So in this instance, we would say that there is no solution. Great. And finally is the case of overlapping lines. So if we have one line and then we go ahead and start to graph the next line and we realize, this line is, I'm going to make it in pink and dot it, it was right on top of the other line. So those two lines coincided. So how many places do they intersect? They intersect here and here and here and all along both these lines. So there are in fact infinitely many solutions. Now this is different than all real numbers, which I know students just really are excited to write all real numbers. But there are points that are like off here in space or off here that are not solutions to this. So there are infinitely many solutions on these lines, but there are points that are not solutions. So that's why we say infinitely many solutions, not all real numbers. So let's look at some actual examples. All right, so these first pair are two equations, both written in slope-intercept form. So to graph slope-intercept form, we start at the y-intercept. So in this case, for the first equation, is up 6. And then the slope is 2/3, so we go up 2 and over 3. And there's our next point. Now, I do recommend that you continue to make more points following the pattern than just 2. And I'll show you why in just a second. So I'm going to follow that pattern in both directions, really as far as I have room for. Terrific. So there are all the points that fit on our graph space. Ugh, let me try that again. Not the worst, but not the best. Okay, so there's our first line, and let me change colors here. Let me graph our second line. So this one starts at down 1. So here, you, by the way, should be using a ruler if you are not doing this digitally. And it has a slope of -5/3. So that's going to go down 5 over 3. Oops, didn't mean to make that extra point there. So there's our point. Don't have any more room to the right, but we can kind of do this pattern backwards. So we can go up 5 over 3, and oh, we see that there was actually a point there from our other line. And so that's why it's helpful to keep following the pattern in both directions. I can even follow it again, 5 and 3 There we are. So we'll connect all of our points here, and again, rulers are important because we want to find the exact point, and if your lines are not perfectly straight, you might not find the actual place where they intersect. So we see visually they intersect here, but it is important that we actually name this point. And this point's name is -3, 4. So we'll put that as the solution to this system of equations. Terrific. Let's try at least one more here together. Here we see another set of equations written in slope-intercept form. The first equation starts down 5, and it has a slope of -1/6, so down 1 and over 6, which means up 1 and to the left 6. So there are our points for the first, and we'll change colors here, and we'll do the next one, which starts up 2, but it goes down 4 over 3. So there's the first point, down 4 more, to the right 3. We see that it lands right on top of that point there. We have room for one more over there, and we could go backwards this direction more, but since we have identified the place where they're going to intersect, I think we're good enough. So we'll connect these lines, these dots, to make the second line, and we'll name the place where they intersect, which down here is -6, 6. Perfect. So that's two examples. These ones were both given in slope-intercept form, the equations, and we found the point where they intersected, and we labeled that point as the solution to the system. Let's just look at a few other situations just to make sure we've covered all kind of examples here. So let's look at number 3 here. So for the first graph, it starts up 3 and has a slope of 1/5, so it goes up 1 over 5, up 1 over 5, and we can go down 1 over 5 and down 1 over 5. So here's our first line. Great. And when we go to get our second line, it starts at +4. So right there, it goes up 1 over 5. And you might have been able to tell this right away because you remember that equations with the same slope are parallel. So we saw the same slope in both of the equations, so yes, these are parallel lines. You are going to still have to graph them because, you know, I'm mean and evil. But also just further proof of what we actually can see with the slopes here. So these are parallel, so there is no solution. They will never intersect. Let's try out an example where we are given equations not in slope-intercept form. So let's look at number 7, for instance, here. Okay, so on number 7, the first equation, 2x plus y equals -8, we can find we could certainly solve this for y and graph it as a slope-intercept form equation, but I'm going to go ahead and use the intercept method. So if x is 0, then y would be equal to -8. And if y is 0, cover up the y there for a second mentally, divide by 2, we get -4. Okay, great. Let's do the other equation. So if x is 0, don't forget the negative here, so divide by -1 and we get -2 for y. And if y is 0, we plug in 0 for y, so we divide both sides by 4, and we get 1/2. Oh, that's mean. But we can do it. All right, so the first line has 0, -8, and -4, 0. 0, -8 is down here, and -4, 0 is right there. So here's going to be our first line. Now, notice we don't have as many points when we graph with the intercepts. But if you kind of think about it, we went down 8 and over 4. You can kind of realize we're going down 2 over 1. So you could even fill in some of the points that would be along the way here between those points and continue that back in either direction. So here is our top equation there. All right. And then our second equation, 0, negative 2, down here, and 1/2, 0. So 1/2, something like there. So I can see I'm going up 2 over a half. So I can go up 2 over a half again and find my next point, which really means I'm kind of going up 1 over 4. So I can go down 4 over 1, and there's my next point. So just following that pattern will help us to find more places where the line is and then find the point of intersection. So this is that point of intersection down here. -1, -6 is our solution. All right, so this is how we solve system of equations by graphing. Next time we'll look at how to solve systems of equations by substitution.